Convergence rates. As we have discussed above, the law of large numbers implies that the profit of the random sampling auction, say in the case of digital goods, is asymptotically optimal as the number of bidders grows. In this section, we study the rate at which the auction approaches optimal performance. The theorem we prove will enable us to obtain a precise relationship between the complexity of the class of outcomes considered by RSOP and its convergence rate. The results in this section will also give us a framework for evaluating the performance of random sampling-based mechanisms in very general contexts. We make our discussion concrete using the example of the digital goods auction problem. Recall that RSOP uses a subroutine that computes the optimal sale price for the bids in each partition of the bidders. Suppose that we allow the auctioneer the ability to artificially restricted prices to be in some set Q. For example, the auctioneer might also only sell at integer prices, in which case Q would be the set of integers. The auctioneer could further limit the set of possible prices, for example, by having Q be powers of 2. We will see that different choices of Q will give us different bounds on the convergence rate. Given Q, we define RSOPQ as the random sampling auction that computes the optimal price from Q on each partition and offers it to bidders in the opposite partition. We make use of the following notation. Let Q of Bi be the payment made by bidder I when offered Q little q in fancy Q. That is, Q of Bi equals to Q if Bi is greater than or equals to Q and Q of Bi equals to 0 otherwise. Let Q of B equals to the summations of Q of Bi summing for all index I. Finally, define the OPT Q of B equals to the argument of the maxima of Q of B, where the maxima is taken among all possible little q in fancy Q, as the Q that gives the optimal profit for B, and the optimal fancy Q of B be this optimal profit. So that is, OPT fancy Q of B equals to the maxima of little q of B for all little q in fancy Q. The bounds we give in this section show that the rate at which the profit of RSOPQ of B approaches OPTQ of B with some measure of the size of the market. The measure we use is OPTQ itself, as this gives us the most general and precise result. Thus, these results show the degree to which RSOPQ approximates OPQ as OPQ grows large in comparison to H, an upper bound on the payment of any agent and the complexity of Q. Definition 13.28. Given partitions B' and B'' price Q in fancy Q is epsilon good if Q of B' minus Q of B', the absolute value of the difference between these two outputs of Q is less than or equals to epsilon times OPT fancy Q of B. Lemma 13.29. For B and H satisfying Q of Bi which is less than or equals to H, for all I, if bids B are randomly partitioned into B' and B', then Q is not epsilon good, with probability at most 2e to the minus epsilon squared times OPT Q of B over 2H. The proof of this lemma follows from McDiarmid's inequality, see exercise 13.5. The following is the main theorem of this section. A natural interpretation of H is an upper bound on the highest valuation, i.e. H equals to the maxima of Vi, where the maxima is taken among all possible index I. Theorem 13.30. For fancy Q, B, and H, satisfying that Q of Bi is less than or equals to H for all Q and I, and the OPT Q of B which is greater than or equals to 8H over epsilon squared times ln of 2 times the absolute value of fancy Q over delta. With probability 1 minus delta, the profit RSOPQ is at least 1 minus epsilon times OPT Q of B. Proof. Assume that OPT Q of B is greater than or equals to 8H over epsilon squared times ln of 2 times the absolute value of a fancy Q over delta. For random partitioning of B into B prime and B prime prime, lemma 13.29 implies that the probability little q in fancy Q is not epsilon over 2 good is at most delta over the size of fancy Q. Using a union bound over little q in fancy Q, we have that all little q in fancy Q are epsilon over 2 good with probability 1 over delta. Let q prime equals to OPT fancy Q of B prime, q prime prime equals to OPT fancy Q of B prime prime, and the q star equals to OPT Q of B. By definition, q prime of B prime is greater than or equals to q star of B prime, and likewise, q prime prime of B prime prime is greater than or equals to q star of B prime prime. Thus, q prime of B prime plus q prime prime of B prime prime is greater than or equals to q star of B, which is equals to OPT fancy Q of B. If all q are epsilon over 2 good, certainly q prime and q prime prime are. Therefore, q prime of B prime prime is greater than or equals to q prime of B prime minus epsilon over 2 times OPT fancy Q of B, and q prime prime of B prime is greater than or equals to q prime prime of B prime prime minus epsilon over 2 times OPT fancy Q of B. Thus, we conclude that our auction profit, which is q prime of B prime prime plus q prime prime of B prime, is at least 1 minus epsilon times OPT fancy Q of B with probability 1 minus epsilon, which gives the theorem. Notice that this theorem holds for all epsilon and delta. In particular, it shows how big the optimal profit must be before we can guarantee a certain approximation factor. Of course, in the limit as the optimal profit goes to infinity, our approximation factor approaches 1. We refer to the lower bound required of optimal profit, OPT fancy Q, in the statement of the theorem as the convergence rate. Indeed, if the agent's valuation are between 1 and h, the lower bound on the optimal profit can be translated into a lower bound on the size of the market needed to guarantee the approximation. Let us now consider a few applications of the theorem. Suppose that fancy Q equals to the set 1, 2, 3 until h. Then the size of fancy Q equals to h and the convergence rate to a 1 minus epsilon approximation with probability 1 minus delta is big O of h times epsilon to the minus 2 times log of 2h over delta. If instead the fancy Q is power of 2 on the interval between the closed interval of 1 and the h, then the size of fancy Q is equals to log h, and the convergence rate for constant epsilon and delta is big O of h times log h. It is worth noting that the particular bits B that are input to any particular run of RSOP fancy Q may further restrict the set of possible prices in fancy Q that can be selected, say to some subset Q prime. We can apply theorem 13.30 retrospectively to input B to bound the performance of RSOP Q in terms of the size of Q prime. For example, in the original RSOP auction, we consider all real numbers as prices. Yet OPT of B is always one of the bits. Thus, using fancy Q equals to B1, B2, B3 until Bn, and noting that the size of fancy Q equals to n, tells us that the convergence rate of our original RSOP digital good auction is big O of h times epsilon to the minus 2 times ln of 2n over delta. Even better bounds are possible using a notation called gamma covers. Corollary 13.31. For fancy Q prime B and h satisfying Q of Bi is less than or equals to h for all Q and I, OPT Q prime in fancy Q prime for all subsets B prime of B, and OPT fancy Q of B, which is greater than or equals to 8h over epsilon squared times ln of 2 times the size of fancy Q prime over delta. With the probability 1 minus delta, the profit of RSOP fancy Q is at least 1 minus epsilon times OPT of fancy Q of B. Lemma 13.29 and Theorem 13.30 are quite general and can be applied, as written, to a wide variety of unlimited supply auction problems with rich structure on the class of allowable profits, allowable offers, fancy Q. Three examples are attribute auctions and combinatorial auctions.